Hi class, this is Dr. O'Connor. Here we're going to talk about chemical equilibrium and Le Chatelier's principle. So first let's talk about what a reversible reaction is. Here we have acetic acid and ethyl alcohol react to produce ethyl acetate and water. And notice in the forward direction, the forward arrow corresponds to the forward direction. We have the reactants acetic acid, ethyl alcohol, producing ethyl acetate and water. Now, notice there's another arrow. This is the reverse reaction. And what will happen is after some time, the ethyl acetate and water will then form ethyl alcohol and acetic acid. So you have this forward reaction producing the ethyl acetate and water, and then the reverse reaction producing the original acetic acid and ethyl alcohol. So many of the reactions in everyday life are reversible. And we define a reversible reaction as a reaction that can go in either direction. Chemical equilibrium is defined as a state in which the rates of forward and reverse reactions are the same. Not the concentrations of reactants and products, but the rates of the forward and reverse reactions. Now, I do want to stress that equilibrium is dynamic. That means that all the substances are continuously being formed and unformed at the same rate. So even though to the eye you might not see any changes taking place, they are. So let's take a look at this plot here. We have reaction rate on the y-axis and then progress of the reaction on the x-axis. So in the beginning of the reaction, the rate of the forward reaction is very fast. And then notice it starts to slow down. At the same time, at the beginning, the rate of the reverse reaction is very slow, but then as products begin to form, then we see the rate of the reverse reaction increases. And at some point, we see that both the reaction rates, the reaction rate for the forward and the reaction rate for the reverse reaction, become equal to one another. This is equilibrium. Let's take a look at some equations and then we'll talk more about equilibrium. So let's say I have an equation in this form. The lowercase letters are the coefficients, and what I can do is I can write an equilibrium equation. The equilibrium constant K, that's represented by an uppercase K, and that is we have the product concentrations in the numerator and the reactant concentrations in the denominator, and notice the coefficients become exponents. So this is how we write an equilibrium constant expression, and we'll practice some of these in a moment. Now, as I said before, at equilibrium, the forward and the reverse rates of reaction are equal, but not necessarily the concentrations. In fact, you might have higher concentrations of reactants and lower concentrations of products, or vice versa. So let's talk a little bit about the value of K. K must be experimentally determined, and we do have values of K for certain experiments. You can find them in handbooks and tables and those types of materials, or even journal articles. But I will tell you that the value of K varies with temperature. Most K values are reported at a temperature of 25 degrees Celsius. Now here's something you're really going to love. When we calculate an equilibrium constant, K, we don't have to worry about units. This is the one time in chemistry we don't have to be concerned with the units. And concentrations are in moles per liter, so it's molarity. And you've all been in the lab, you have seen that concentration unit before. So anytime you see a substance in brackets, that means the molar concentration, or the concentration, is moles per liter. Okay? Or we use capital M, which is molarity. We'll talk more about molarity a little bit later. So molarity. So let's say I have something that's 0.1 molar. What that means is, let's say that's potassium chloride. What that means is I have 0.1 moles of potassium chloride in 1 liter of solution. Let's go up here for a moment. At equilibrium, the ratio of products to reactants will be equal to a constant value. That doesn't mean that the concentrations are equal to one another. It means that this ratio is equal to a constant value at a given temperature. So we have this reaction here between sulfur dioxide and oxygen to produce sulfur trioxide. I write the equilibrium expression. So again, it's the product that goes in the numerator, and the coefficient becomes the exponent, and the reactants in the denominator. And again, the coefficients become the exponent. Now, it turns out for this reaction at 729 degrees Celsius, the equilibrium constant is 429. This would have been determined experimentally. At a temperature of 729 degrees, this ratio of products to reactants is going to be equal to a constant value of 429. Now, it turns out that you can determine the position of equilibrium from K. So in other words, are there more reactants present at equilibrium? Are there more products present in equilibrium? Or are there equal amounts of product and reactants at equilibrium? In fact, let's go back to this expression here. All right. Concentrations here at equilibrium are going to be such that this ratio is equal to 429 at 729 degrees Celsius. Well, what does that mean? It means that in my reaction vessel, I am going to have all three of these substances. There'll be SO3, there'll be SO2, and oxygen. So all of the reactants and products are in the reaction vessel. The question is, will there be more of this and this, or more of this? And that's what K can tell us. The value of K can tell us that. If you have a value of K that is much larger than 1, then you can basically say that you only have products present at equilibrium. In other words, the reaction goes to completion. It's not reforming reactants. Now, if you have a K that's between 1 and 1,000, what that means is you're going to have more products than reactants that are present at equilibrium. So for our example, K is 429. So you're going to have a lot more of this and a very little bit of sulfur dioxide and oxygen. If you have a K between 1 and 0.001 or 10 to the negative 3, that means there are going to be more reactants than products at equilibrium. A K smaller than 10 to the negative 3, that means basically not much of a reaction occurs. You're going to have very small amount of products. So here's a nice little tool that you can use to determine that. So if I tell you that I have a K equal to 2.4 times 10 to the negative 5, then K is much smaller than 10 to the negative 3. So you essentially have mainly reactants in your reaction vessel. If I have a K equal to 10 to the 2 or 100, then I'm going to have more products than reactants. Okay? So let's go ahead and write some equilibrium equations for the following. So we're going to write some equilibrium constant expressions. So first thing I need to do is make sure my equation is balanced, and it looks like it is. So I'll write this. K is equal to, what I want are the products. So we have the bromine, and the coefficient is 1, so we don't include that as an exponent. Multiply that by the concentration of the fluorine, and that's to the third power. Remember, coefficients become exponents. And then we have our reactant, and again, the coefficient becomes the exponent. So this would be the equilibrium constant expression for this reaction. Let's go ahead and take a look at a very familiar reaction here. So K will be equal to the concentration of ammonia to the second power divided by the concentration of nitrogen multiplied by the concentration of hydrogen to the third power. Practice writing those equilibrium expressions. Before we go any further, I will tell you right now that in the equilibrium constant expression, we can only have gases and aqueous substances. We do not see solids or pure liquids in the equilibrium constant expression, and that's because their concentration is constant. Okay, so for example, you would never see liquid water in an equilibrium constant expression, but you would see water in the gaseous form. Let's take a look at this. We have our ammonia and water, and we have the products, ammonium ion and hydroxide ion. So we check to make sure that the equation is balanced. It is. And then we can write our equilibrium constant expression. If I were to tell you that K was equal to 1.6 times 10 to the negative 5 at some temperature, the temperature should be reported here. I did forget to put that in, but we'll just say at some temperature. So K is 1.6 times 10 to the negative 5. Are there going to be more products or reactants at equilibrium? So they're asking, are products or reactants favored at equilibrium? Well, this is 10 to the negative 5, so that is much less than 10 to the negative 3. So in this case, reactants are favored at equilibrium. So we mainly have reactants and very small amounts of these. Let's do another problem. Let's consider this reaction. We have hydrogen iodine to produce hydrogen iodide. And first I'm going to make sure that my equation is balanced. And here we're given the equilibrium concentrations of hydrogen iodine and hydrogen iodide. They want us to calculate K. First thing I'm going to do is write my equilibrium constant expression. So K is going to be equal to the product, and that's squared, divided by the product of the reactants. So now I'm just going to plug in the concentrations. So for hydrogen iodide, we have 0.507 moles per liter. We don't have to worry about units. Make sure you square that. And then for hydrogen, I have 0.051 moles per liter. And for iodine, we have 0.174. And then I just go ahead and plug this into my calculator, which of course I can't find. I'll be back. Here we go. So I'll take 0.507, I'll square that, I'll divide that by 0.0510, multiply that by 0.174, and I end up with a K equal to, our reactants or products favored. Well, K is greater than 1, so obviously the products are favored. Okay, and it's easy to tell from the expression, right? If this expression is greater than 1, then that means the numerator is greater than the denominator. If this expression is less than 1, that means your denominator is greater than the numerator. So go ahead and practice those. I'm going to talk about something called a Chatelier's principle. And we can actually change the direction that is favored. And, we have to do this in industry all the time. So here's what a Chatelier's principle states. If a stress is applied to a system at equilibrium, the equilibrium is going to shift in the direction that relieves the stress. Okay, what do we mean by stress? A change in concentration, pressure, volume, or temperature. So if a system is at equilibrium, we can change concentration, we can change the pressure by changing the volume, or we can change the temperature. That'll disturb the original equilibrium. And then the equilibrium or the reaction is going to shift in such a way as to remove that stress. Now, before we go into this, I just want to let you know that a catalyst will not affect equilibrium. Remember, a catalyst only increases the rate of reaction by lowering the activation energy. So if we add a catalyst to a system at equilibrium, it will not affect it. We'll just get there faster, but it's not going to affect the equilibrium. So let's take a look at what happens if we change the concentration. So here we have a reaction, carbon monoxide and hydrogen, to produce methanol. Okay? So let's say we increase the amount of carbon monoxide. And again, the system will be at equilibrium. I said it's going to shift in such a way as to remove that extra carbon dioxide. So it'll shift in such a way as to remove that extra reactant. So how is that going to happen? It's going to have to shift to the right to produce more methanol. Okay? If I were to decrease the concentration, so I'm taking it away, then the system is going to shift to replace what I took away. So that's how a Chatelier's principle works. If you add something, the system shifts in such a way as to remove it. If you take away something, the system shifts in such a way to replace it, and then we'll establish a new equilibrium. Okay? So I decrease the concentration of this, the system then will shift to the left. Okay? Will form more carbon monoxide, and then the system will establish a new equilibrium. If I increase the amount of hydrogen, then the system will shift to remove that. It'll shift to the right to make more methanol. Now, what if I remove some methanol once the system is at equilibrium? Then the system is going to shift to the right to replace that methanol. Now, here's what we do sometimes in industry. We will continuously remove the product so that the system never reaches equilibrium. So in other words, as long as you don't run out of reactants, then you'll continuously make more product. So that's a trick that's used in industry all the time. So, and that's what I say here. If reactants are continuously supplied or products are continuously removed, equilibrium is never reached. So that means we can force the reaction to favor more product, right? Which would be in your best interest if you owned a plant that makes ammonia. Le Chatelier's principle predicts that an increase in temperature will cause an equilibrium to shift in favor of the endothermic reaction so that additional heat is absorbed. So let's take a look at this. An endothermic reaction is favored by an increase in temperature. An exothermic reaction is favored by a decrease in temperature. Let's do this a little bit differently. Obviously, because heat is a product, we know this is an exothermic reaction. Okay? So you can think of the heat here again as a product. So if I remove a product, what's going to happen? The reaction will shift to the right to replace that product. If I add more heat by increasing the temperature, then it wants to remove that. It's going to shift to the left to form more reactants. If I had an endothermic reaction, and I'll just write a general reaction here. So I have A plus B. Endothermic means that heat would be a reactant. Okay. Now, if I were to increase the temperature, okay, so again, I'm increasing a reactant, it's going to shift to the right to remove that heat. On the other hand, if I lowered the temperature, I'm removing the heat, then the reaction will shift to the left to replace that heat. So that's how that works. Remove, again, as I said, when you add something, the system shifts in such a way as to remove it. When you take away something, it shifts in such a way as to replace it. Increasing the pressure by decreasing the volume will shift their equilibrium in the direction that decreases the number of molecules in the gas phase and decreases the pressure. So for example, on this side of the reaction, I have 4 moles of gas. On this side of the reaction, I have 2 moles of gas. So if I increase the pressure, this is going to shift in the direction that decreases the number of moles of gas. So in this case, it would go right. So I increase the pressure, it's going to go to the side with fewer moles of gas. If I decrease the pressure, it'll go to the side with more moles of gas. So I decrease the pressure, this will shift to reactants. As I said before, addition of a catalyst does not affect equilibrium. It only reduces the time it takes to reach equilibrium. Let's do a little problem here. And we'll this particular reaction, again, I can't remember the temperature, but anyway, we have sulfur dioxide oxygen to produce sulfur trioxide. So my question for you, we see that this is exothermic. My question for you is this: is the yield of sulfur trioxide at equilibrium favored by higher or lower pressure? Well, let's count the number of moles of gas. We have 3 moles on this side. We have 2 moles on this side. So it's asking, is it favored by higher or lower pressure? Well, if I increase the pressure, then it'll shift to the side with fewer moles of gas. So it would be favored by a higher pressure. Higher or lower temperature? Well, this is exothermic, so we can think of heat as a product. So if I lower the temperature, that means I'm removing the heat from the product side. So then the reaction would shift to produce more sulfur trioxide. So lower temperature. If I were to increase the temperature, okay, and again, we're thinking of the heat as a product because it's exothermic, then if I increase the temperature, then again, it's going to shift in such a way as to remove that heat, so it would shift to the left. So this would be favored by a lower temperature. Addition of a catalyst, no change. Catalyst does not affect equilibrium. So how will the following affect the yield of sulfur trioxide if we add more oxygen? We're adding a reactant. The system will shift to the right to produce more sulfur trioxide. So this will increase the yield of sulfur trioxide. Continuous removal of sulfur trioxide. Well, if we continuously remove it, the system never reaches equilibrium. And I will keep producing sulfur trioxide until I run out of reactants. So that would increase the yield of SO3. Removal of oxygen. So I remove some oxygen. I'm removing a reactant. So the system will shift in order to replace that reactant. It will shift to the left. So if I remove oxygen, I will decrease the yield of sulfur trioxide. What if I add some sulfur trioxide to the reaction vessel? So I increase this concentration. Again, the system's going to shift to remove it. It will shift to the left, so that would also decrease my yield of sulfur trioxide. Anyway, that's it for Chapter 7. If you have any questions, please contact me, and I'd be more than happy to help you. Everybody have a great weekend.